Welcome to class, session 23. What I'd like to do today is I'd like to pick up and start talking a little bit about quality control, and hopefully today I'll finish quality control and give us a little bit of a lead into the maturity method. There is currently no homework assigned. However, you will be getting one soon. So don't fret or anything like that. Don't cry yourself to sleep all weekend. There will be a new homework probably next Monday or Wednesday that'll go up online. I apologize. I've got a little bit of low energy going on today. I'm about ready to take a nap, so if I curl up here and take a nap, feel free to pop out for the rest of the class or take a nap alongside. We'll all wake up at the end when the music comes back on. But what we want to do today is we want to finish up talking about quality control. We started off last class talking about the idea the concept of quality has really changed. So when we go to talk about quality control in the concrete industry, what we're really talking about is making sure that things are the same from truck to truck, from batch to batch, making sure that things are reproducible in terms of size, in terms of strength, in terms of material properties, and that's really what we're trying to do. So we looked at the slide that had 6 items of quality control and production operations, and really there are several things that we want to make sure that we capture. We want to know what the criteria are for purchasing. We want to know something about the engineering and the drawings that are being used, the calibration of the equipment, inspections, the testing, keeping records. All these are important concepts. So remember, we said that there's more to life in purchasing than just looking at the bottom line, and part of this is making sure that you're getting what you're after. Make sure that you understand what you're going to do in the case. Make sure everyone understands what you're going to do in the case where your materials don't meet specifications. One of the reasons why this is going to become more and more important is because, as I mentioned, you are seeing a move away from prescriptive specifications into performance specifications. And one of the real things that hangs this up in the construction industry is if you are the ready-mix producer and you're going to be held to performance specification criteria, how do you ensure that you get the right aggregates coming from your supplier? Is it just good enough that they hit the ASTM numbers, or do you have other things that you want them to hit so that you're getting the right gradation so that you can make a concrete with the right strength, the right low standard deviations, low variability? Make sure that you understand that if it's not hitting specification, it's going to be returned, or you've got some other policy that's there so that everybody's aware of it right up front. We talked about the idea of double checking. Here, the idea of just sampling. Many times the construction industry will help you out considerably. It'll help you considerably because now you have a record of the materials, or even if you don't test it. I used to work for a company, we used to just pull aggregate samples, and I would say that 80% of them were never even tested and they would be dumped back out. But if there was a problem while they were while it was going down, they actually had the materials that were going in through the process. Equipment calibration, you got to make sure the equipment's calibrated properly. Got to make sure that everybody's following the same standard procedure for doing testing. Now, everybody's hearing that music too, right? Okay, I was hearing music before that nobody else was hearing in the room, so everybody heard that now. So, pre-pour inspections, a couple of things that we really need to make sure of. Checking for any missing spacers. You really want to make sure that your reinforcing steel is going to end up where it needs to end up. Make sure it's tied in. Make sure that it's not flopping around in the breeze. The other thing you want to make sure of is when form oil, for example, is sprayed in the forms. Form oil is there to keep the concrete from bonding to whatever the form oil is touching. So form oil belongs on the forms, not on the reinforcing steel. If you want it to bond to the reinforcing steel, you got to make sure that it's not being sprayed inappropriately or incorrectly. There shouldn't be things like Burger King wrappers and other things like that in the forms. Occasionally you'll see them, they accidentally get into the forms so they don't blow around on the construction site, but you want to make sure that everything is clear. Making sure that the reinforcing steel is installed as specified is really a crucial criteria because once it's cast, it's a major issue to go back in, take it out, and get it right. Service penetrations. Here, if you've got anything that's going through a poured concrete wall, through a poured concrete floor, you can save quite a bit by making sure it's installed in the correct spot from the beginning. reminding everybody of their jobs, and then discussing the finishes. Now, as we ended, we said, what are some of the things that you should be recording? I think one of the most important things that a quality control person is really charged with doing is keeping incredibly good records on the materials that are coming in, on all of the equipment that they're using. So some of the materials that you'll be keeping records on are cement mill certificates that are coming through, keeping a copy of those with each truck of cement that comes through, aggregate reports including gradation information and moisture from your supplier. In addition, you may be running your own tests. You may be running your own tests just to make sure that you're getting what they claim that you're getting. Because I will also tell you that when I was this inspector for the state in Pennsylvania, I saw several aggregate producers who had nice mimeographed, which gives you a little bit of an idea on the era at which this was happening, or photocopies with the gradations already filled in for you on their material. And they were the same for the last 15 to 20 years. All right? Now, they may be very good and they may be hitting the exact same material all the time, or they may not actually be testing it and sending it out to you on each site. So you want to make sure that you're keeping track not only of the information they send so that you've got some information on what they claim they're providing, but also the tests that you're getting. And if there's any big differences, you want to make sure that people know what's going on. Chemical and mineral admixture certifications, as they're coming through, they should be kept on file. Reinforcement supplier reports, just like we'll see cement mill certificates, you'll get the same thing for reinforcing steel. Any accessories that you're putting in to the concrete. Batch records, ready mix tickets. You'll see that people will carry these around as a badge of honor. In addition to the badge of honor of the big clip of tickets that you've collected that day, they should be properly filed. Because one of the things that's always fascinating is the most interesting ticket is the one out of the 300 tickets that's not there. Okay, so you want to make sure that they're properly filed. Work orders, product drawings, if a change is made, an email change or anything like that, you want to make sure that you've got it on file so that everybody knows why you decided to take the reinforcing steel out. It's very difficult after the fact to go back and say that Bob said take the reinforcing steel out and we'd be okay. Bob usually doesn't remember that unless you've got it in writing. It's a little bit like what we see happening in Washington, D.C. now. No one can remember if they were at a party or not at a party until a picture surfaces. And then, I remember being at that party, but I didn't do anything bad at that party. Okay, so same types of things. Keep the product drawings. Equipment calibration reports. If you get into a point where you're fighting over results, making sure that your equipment's calibrated is incredibly important. Air meters, thermometers, clocks, things like that are incredibly important to keep up to date. I worked for one producer. The clock was off and an inspector was ready to send back 18 trucks because the automatic clock was off at around the time of daylight savings time because all of the times were off. Concrete, when it showed up on site, was out of time, and he wanted to send everything back. So making sure that everything is accurate is incredibly important for things like that. Thermometers, you can check them pretty easily. There are some certain temperature points that are very easy to find with a thermometer. 100 degrees Celsius is pretty easy to find. Most of you could probably figure out how to do that all on your own, right? You could try to boil water on your own, and maybe you'd be able to be successful and make sure your thermometers are on target. Keeping track of the test results, and I'll show you a few simple ways to keep some of that information. And then personnel training. If you have personnel who are being trained, this is becoming a bigger and bigger issue. ACI certifications, level 1 testing certifications, level 2 testing certifications, non-destructive testing certifications, precast or PCI plant certifications, making sure that all that information is documented and that you've got access to that information if you had to bring it up. A little bit of a side note, but it really comes down into the importance of recording. A few years ago, there was a producer who was being held to a very strict strength requirement on concrete pavements, and as he started to produce his concrete, all of a sudden he started to realize that they weren't getting the strengths that they normally get. This is the same mix that they've used over and over again, and they started to try to figure out what was the issue. The aggregates seemed okay, mixing process was the same as what they were doing before, and they were convinced that it was an issue with the cement. So they pulled some cement samples, they looked at the mill certificates. The mill certificates looked exactly like they always had. They got one about a week later, and all of a sudden all the C2S, C3S fineness numbers were all different. And one of the things that was very helpful is when they were starting the process of discussing whose issue it was now that the concrete wasn't strong enough, the supplier who came in with 700 mill certificates from the last batches of cement they've gotten, saying we should have been notified that there was a change coming, it was a much stronger case than going in and saying, oh, we don't know what the issue is, we don't know what the problem is, let's all try to work it out. They came in and they said, we track this, we look at it every day, we're looking for changes, no one let us know that this was happening, we need to know this up ahead of time. Now, if I asked each person in the room to measure quality, most of you would tell me how you would measure the quality of concrete. And if this was a freshman or sophomore class, the first thing that they want to do is the first thing that every civil engineer wants to do. They want to break something. Let's go to the lab and let's squish it, let's squash it, let's break something. So first thing that everybody typically wants to try to do is to take a cylinder, throw it in between two platens, use a lot of hydraulic pressure to try to break this. It'll explode, it'll be fascinating, there'll be dust all over the place, and now we've got a number. This concrete has a compressive strength of 4,795 psi. What do we do with that? Well, most of us are a little confused, but we had a good time the first time we broke something, so let's break something else. And we'll typically do it again. We'll take another cylinder, we'll get something like 4925 psi, and now we've got a big issue because those numbers aren't exactly the same. And it's very, very unlikely that you're going to get a number that's exactly the same. So most people look around and they say, I've got two numbers. The one thing that I know how to do is I know how to take an average. So if you don't know how to do that on your own anymore, you could find that there's an average key in Excel, and you could take the average and you would know that this concrete has exactly 4,860 psi compressive strength. Whew. It's an exhausting day. We finished this up now. What do we do with this information? Well, what I would say is the average strength tells us something, but it doesn't tell us everything. And averages can be somewhat misleading. Here we see a picture of the Mississippi River. On average, the Mississippi River is 11 inches deep. If you own a paddle boat, that information doesn't help you out an awful lot. All right. So what we really want to know is we really want to know something about the statistical distribution of the strengths that we're getting. We want to know something about how the strengths are distributed, how the thickness is distributed, where are the thick sections, where do we have a lot of variability. So one of the ways that we can start plotting some of these results is we can see something like the number of occurrences in a particular range. So here we may have a range from 625 psi in flexure to 650 psi, and we can count the number of specimens that have broken in a particular range. And we could get something like this, which gives us a distribution of the strength. So in addition to calculating something like our mean value, which we'll see here, we could also get this distribution which tells us a little bit about how much variability we should expect from beam to beam. Now this data is actual data from a concrete paving project where they're looking at the beam breaks that are coming back and trying to get an assessment of the quality control and the variability that exists. Now the one nice thing is you can take these numbers of occurrences and you can start to plot this information out to define variability in a little bit more meaningful way. So that same information that we just saw with the number of occurrences, you could actually convert by dividing through by the number of tests. And all of a sudden now you have a histogram that has the percent of tests falling in each region. You could fit a bell-shaped curve or a normal distribution of that, and you could start to properly define the mean and the standard deviation for this mix. So now all of a sudden we're starting to say we've got a mean strength, we also have information on the standard deviation, and we could start understanding that one standard deviation contains about 70% of the overall population. Two standard deviations is about 96% of all the information. And by the time we're up to 3 standard deviations, we've covered almost all the test results that we're going to get. Now, while this is nice and this is the way that we normally look at standard deviation, we normally look at distributions, I'm going to ask you to challenge the way that you look at the world. And I'm going to ask you to turn your head sideways as we move to the next graph. Because I think what we're going to see is there are other ways that we can start monitoring monitoring material variability in a little bit more detail. So in the ideal world, quality is going to be monitored by someone who's not involved in either production statistics, we've produced 10,000 yards of concrete today, or marketing. It is very, very detrimental to reputation to have either someone who is involved in the sheer fact that they need to push out a lot of volume, or someone who is trying to sell the product who's responsible for keeping tabs on making sure that you're putting out a good quality product. There's the potential for a conflict of interest in what they're doing. So you want to make sure that you try, in an ideal world, to make sure that you have someone separately in control of looking at the quality, and just their primary focus is on quality, while other people may be looking at other aspects. Now, this is an ideal world, and many of you will find that there are small companies where they have one person who's qualified to monitor it, to do the production, to do the quality control. He's really good at making coffee as well. So you'll find that there are smaller operations. You always need to be able to compare and in your own mind and understand what their motivations are as they're giving you some of this information. Comprehensive system. Most of the companies that'll be looking at this will have something like a quality manual, what they do, how they monitor their processes. That is something that can really help, and we'll talk a little bit more about that towards the end. Again, the quality in an ideal world, you'll have detailed records of what's going on. You'll have training manuals, or you'll be able to say how everyone is trained. And then you'll have formal procedures for how you deal with goods that didn't meet up to satisfaction. Now, I'm going to start to talk a little bit about quality control and quality assurance. So in almost every state in the nation, all 56 of them according to FHWA, or 58, all right, they do a process called quality control, quality assurance. In Indiana, we do quality assurance, quality control. I don't get it either. All right, everyone else does QC/QA, we do QA/QC in Indiana. The big differences here are, when we're starting to talk about quality assurance, the owner is going to establish the requirements that they want. And this is typically a mean and a range. So they're going to say we want 3,000 psi concrete with a standard deviation of 300 psi. They've established the level of quality that they want. They've said what the mean is going to be. They've said what the range is going to be. They've said this is really the performance, or these are the properties that we want from that particular concrete. In an ideal world, the contractor is then going to go ahead and develop a quality control plan. The contractor is going to say, in order to meet that requirement, this is what I'm going to do. These are the steps that I'm going to take in the process to do that. I'm going to do aggregate gradations 3 times a week. I'm going to check my moisture content once a day. I'm going to adjust my moisture content when this, or this happens. I'm going to monitor strength at 24 hours, and I'm going to use that to adjust my mixing practices. All right? The contractor will then take samples while they're producing the concrete, compare them to targets that they have established. So they're going to take their own samples. I've decided I'm going to pull gradations. I will compare those to gradations that I have set that will enable me to make good quality concrete, and I will use this information to do something. All right? And I think this is one of the most important components in this whole process. This information is used as feedback. This information helps you adjust your process, helps you adjust what you're doing, to control the process and to make adjustments. So we don't just take tests to practice taking tests or because we really love doing sieve analysis. We run these tests to help control the concrete that's being made. So if we see an adjustment in the finest modulus, we make an adjustment to the concrete. The owner then assures that the contractor has done what they are saying that they are going to do. So the owner would go out and pull random tests. Now when I say random, random has a very specific meaning here. It's not like the owner runs out and says, I feel like testing this for the smell of the concrete or something like that. The owner is going to go out and choose random spots in terms of time and location to sample the material. They're going to make sure that it's compliant, meaning that it's within the limits that they've established from the beginning of the project. There is no feedback on quality assurance other than the materials are good or the materials are not good. Now, I will say that this is the ideal version of the way that this is done. There are a few caveats that go on to this. Typically, the owner does not go out and do simple random tests. They do random tests according to some sort of a process. So if you work for a DOT, they have a random process for sampling, but that random process means that they roll a dice, they flip a coin, and then they go to a chart. They pick a number, go to a chart, and that tells them which load of concrete they are going to go out and sample. The goal is not to be out there picking winners and losers. The goal is to be sampling something that represents the average production. The other thing that I would point out is frequently you do not see quality control being done before the assurance step. And maybe this is why Indiana is the only state that has them in that particular order, although I don't believe that's what's being advocated. The idea here is that the contractor is going to take their own tests, control their own processes, use that information as a feedback, and the only thing the owner is doing is checking to make sure that they have met the requirements. Frequently, the contractors aren't sampling as quickly as they need to. So what happens is, a lot of times you'll see the agency go out, the Department of Transportation, the Bureau of Reclamation, whoever is paying for that job, they will pull cylinders, and the contractor will pull 3 cylinders along with them. Because the contractor is more worried about making sure they did the testing right than controlling the process. And that is not the way that this system is supposed to work. You're not supposed to be learning 3 minutes after the state does their tests what the test is, what they're going to get. You're supposed to know ahead of time that your material is compliant and within the limits. All right, now, when we do statistical process control, we really want to look for 2 different types of variability. We want to look for special and common variation. Common variation is something that happens that's inherent in every process. It describes why nothing is ever exactly the same. So if you take 3 or 4 or 5 cylinders, they may be all virtually the same concrete. They're all going to have the aggregate space just a little bit differently. You're going to get different results from those. This is something that's it's expected. This is why we say we're going to have variability in our strength. We know there's going to be some inherent variability. Special variation is something that happens that is not part of the process. Oh, whoops, we forgot to put cement in. That is a case of special variation that is a cause for concern. All right, so statistical process control is going to help us identify when this special variation has happened and allow us to take steps. So now you can turn your heads to the side. You will notice that if you turned your head 90 degrees, depending upon which direction you turned it, you will either see the normal distribution curve or an upside down version of the normal distribution curve. So on our y-axis now, we have the strength. The green line is our average. Along the x-axis now, we have the percentage of tests. So this gives us a little bit of an information on where we are when we start to talk about the mean value. So this is our mean value, the green line. And then we start to have our 1 standard deviation line or our 3 standard deviation lines. And a lot of times we're going to use things like 2 or 3 standard deviations as really our outside limit where we start to want to do some sort of process control. Now, we could plot this histogram just like you see here, or we could start to plot the data in a slightly different way. And instead of plotting in terms of a histogram, what we can actually do is we can plot this in terms of a running graph. And many places you go, you will see this type of running graph. If they're going old school, they've got something from a mimeograph or a photocopier that's been photocopied so much that you can barely read what's on the axes. And every day that they do a test, they're going to put a little blue or red line, all right, where that test result ran. If it's where that test result landed. If it's someplace that's been updated over the last 40 years, they may have an Atari or Commodore 64 if they're lucky enough, or maybe even something that's running Windows so that they could have Excel. And you'll see them every day they will add a different test result. So the first day, they'll run their test. They will plot the strength that they obtained on the first day. They will do the second day, the third day, the fourth day, and so on and so forth. So you can actually see that a lot of times they'll either have the number of samples listed across on the x-axis, or they'll have the date that the specimen was tested listed across on the x-axis. Now you'll also see that there'll be two other lines. We typically have a line that's the target strength, or the mean that we're looking for, which is drawn here in green, and there'll be some sort of a requirement that is a certain number of standard deviations away from that. And the basic idea is this gives you a quick method of looking at, all of a sudden, is something changing in my process? Now here you can see that the data looks like it's somewhat random. All right, but all of a sudden you could start to see if you did test 65, 66, 67, all right, and they're not showing up on the screen even though I'm drawing them. But if you were to do the next set of tests and all of a sudden they started to drop down like we're seeing here, you could start to say, hey, wait a second, there's something that's going wrong. Maybe we don't have the cement that we thought we had. Maybe our aggregates aren't what we think they have. It's a graphical method, gives you information back in a hurry, and it's pretty useful. Proper quality control procedures will help to avoid big surprises in quality assurance testing. This is quality control done the right way. For those of you who travel through Indianapolis, this is I-65, right around where you can jump off on the Martin Luther King Expressway. This is a project that actually won a national quality award for the concrete pavement that's actually been placed down there. This is the quality control. So these are the beams that the contractor is taking and using this information to control how they're making the concrete. So when the contractor did their testing on their schedule, they test one beam every 3 hours, or one beam every 2 hours, or one beam every 200 trucks. They got this information, which had a mean of 762 psi in flexure and a standard deviation of 49 psi. When the state came through to do quality assurance, their data is shown here in yellow. Now, one of the things that you will notice is the state did a lot less testing than the contractor did. The state, remember, is just saying this is good or this is bad information. When the state got their results, they found out that it was about 752 with a standard deviation of 45 psi. There are no big surprises there. No one is shocked. Everything worked out exactly like we expected because the contractor was out there using this information to control the process. Using this information to control what they were doing. They had a good knowledge. They were doing quality control so that nothing was really a big shock when they started doing testing down the road. We don't take tests for practice. They're actually used. Quality control tests are called quality control tests for a reason. They're there to control the quality of what you're doing. They're there to help you understand the material better, to provide information that what you're producing is what you think you're producing, and to help you to make adjustments as you go throughout the course of your day. We talked a little bit about some of this. We talked about looking at aggregate gradations and how you could use fineness modulus to help you make adjustments. Using water in the aggregates to help you make daily adjustments. All right? Quality control is an active process that has to be done. Now, there are a few different ways that you could use these types of graphs that I've shown you. The first way is truly just to ensure that you're within a band. And I would say that this is what 95% of the people who are developing these types of charts are doing. They are plotting the data points, and they will typically, I will tell you, when I worked for a producer, we had a big line here that was drawn with a Sharpie magic marker, and that was the line you didn't want to cross. All right, that was the no-fly region. If you weren't above that line, you had big problems. And you were just checking to make sure you were staying above that line. Making sure that you're compliant, making sure that you're somewhere within the band. That is one way that you could use this information. The second way is to use this method to really be checking back against your design. Now, individual tests themselves are less sensitive to changes in overall quality because, remember, they have normal variability that's allowing them to fluctuate. You don't want to make an adjustment on any single test. You don't want to go in and say, oh my goodness, this one's a little bit low, let me put some extra cement in, because you're going to be chasing something that may just be the normal variation. What you're really looking for is that special variation, and that's what you're trying to track down. So one way that people do this is they try to use something called a cumulative sum process. And sometimes you'll hear people talk about this as the Q-sum process, C-U-S-U-M. And what they're really doing is they are checking really low tests to make sure that there's no big problems, but they're using a running average and plotting a running average as they're going. And by plotting a running average, all of a sudden they can start to see, hey, if my running average gets to some value that may not be the bargain basement value, but it may be some set point or some target point, there's something that I usually need to do in this system. Now you will notice that there were 3 adjustments that were made in this particular mixture. There was an adjustment that was made each time the red line was hit. And I will tell you that the adjustment that was made each time the red line was hit, one of these was related to air, and one of them was related to the aggregate gradation. So once you start to see that there is some sort of a steady process, you need to track down where that's coming from. There's carbon in the air. We need to add a little bit of extra air entrainment. In one of these particular cases, I believe it was this case in the middle, the air was staying high because there was too much air entrainer, so they had to back that out. The other one, you're seeing a little bit of a change where the gradations are changing. But the basic idea here is you're going to set some target, and when a running average hits that target, then you're going to start to make some sort of an adjustment. Okay? Now, what are some of the practical implications? All right, is there a way to use statistics and use process control for good instead of evil? How would a contractor actually benefit from having a better quality control group? Well, one of the things that we could actually do is we could start to look at what happens if you had a concrete producer who could make concrete with 680 psi, a mean with 680 psi, and a standard deviation of 45 psi. Now the assumption here is that we're going to have about 1 in 1,000 tests falling below the specified strength, and we're going to compare 2 different contractors here. So one contractor has a standard deviation of 45 psi, the other has a standard deviation of 1,000 psi. If both have the same percentage of failures, you would have to design for a much higher strength when you have higher variability. So the lower variability enables you to have a much tighter design. Now what does that mean in terms of practical information here? Here you could be talking about 40 pounds of cement per cubic yard, 50 pounds of cement per cubic yard. There is a real value in being able to take 40 or 50 pounds of cement out of your concrete. It's an economic value to be able to have a better control over the quality. And to give you a little bit of information on this, here you can see the idea of how the target strength would vary based on the standard deviation to make sure that you stay above that 570 psi number. Basic idea is as the variation increases, the strength that you would need to target would need to go up. Now the other thing that you can do is you can start to relate this back. You could start to relate this back to cost, as I was mentioning. So if you wanted to start to try to get better information on costs, and this is not flexural strength, this should be cost here. Cost in terms of money units, dollars, pesos, French francs, all right, whatever you're printing in your basement. All right. Basic idea here is about the lowest you can go for cost is this value down here. You want to try to reduce cement. You want to try to make your aggregates more economically efficient. That's essentially the direction you want to go. This is the cost factor number that we were taking off the previous graph. And as you start to go to higher and higher flexural strengths, as you start having to design for higher and higher flexural strengths, you'll see the cost of that mix starts going up. And you can get information like this. One of the things that's a little bit tricky is everybody says, well, I can't get information like this. I don't know how I would get this. There's information in a book that exists. And some of you in the construction management world probably know what that book is already. Nobody's ever heard of means? RS means. RS means will tell you what the cost of different concretes are with different strengths. And you can get an estimate of what that would mean for an average type of mixture. Now, every particular producer is going to have their own numbers. There are certain strengths that they can hit economically. There are other strengths they can't. But RS means would give you a good, reasonable way to start to look at this. All right, so Opus must have been a contractor because all he was really after was a little bit of consistency in life. And contractors would love to have consistency. All right? They do not want to come in and find a surprise every single day. At least I don't think so. Okay. Now, where does the variability that we have come from? Well, there are several sources of variability. There's the variability in the test machine itself. There's the variability in operators. Here you have variability, even if you have two good operators, they run the test just slightly differently. But you also have what's probably the more important case here, where you've got the person who's very good at running the test and the guy who could care less whether he runs the test right. Right? This is variability that's in the testing process itself. There's the material variability as well and production variability. And what we really want to try to do is we really know that we have some inherent material variability. We have some inherent variability due to the testing process. But what we're trying to do is minimize the production variability as much as we can. Now, you may say, well, this particular plot doesn't have a whole lot to do with my actual life. How would I actually use this information, or how would I start to use this information? We could basically write that the variability or the standard deviation is equal to the square of the testing variation, the inherent material variation, and the production variation. So the total variation that's being measured on any test, if you go to the lab and you take a cylinder, you test that cylinder, the variation that you're bringing out is this particular variation here. All right, when you run the standard deviation on the compressive cylinders that you get. But that's made up of the variability that comes from the testing machine, comes from the inherent material variability, the fact that concrete is heterogeneous, you're testing it with aggregates on a very large scale, and the production variability. What most agencies want to control is the production variability. What contractors need to be very careful of is that they don't set the variation so small that you can't reliably test it. If you started to look at this and you started to plot on any particular axes here, you could start to plot production variability versus measured variability. What you would have is you could have zero production variability, but you're still going to have a measured variability because there's variability in these other processes. And what you would find is a graph that looks something like this. And you want to make sure that they're not setting the specifications so low that you're picking up and you're measuring the variation due to the inherent variability and the testing variability. Common example of where this gets done is in terms of air content testing. You'll see specifications that sometimes come out and they say, well, you have to control your air within 0.1%. Well, you can't control your air to within 0.1%. The variability in the testing itself is 0.6%. All right, so you need to make sure that you understand what some of these variations are. Simple plots like this can help you out quite a bit because it gives you an idea of where you need to be setting some of these values. Controlling all aspects of the production, obviously, you can't run out to the yard every so often, throw a couple rocks in a bag or throw a couple rocks in your pocket and think that you're controlling the material. You need to control every step in the process. Proper training of personnel on how to do this is important, and this becomes more and more difficult as people go faster and faster and as they start to worry about staging projects. It is very infrequent that you're going to be able to go into a large infrastructure project in the middle of a city and lay out all the materials that you're going to use from start to finish and start working your way from one end of the pile to the other during the course of the job. You will find out that people are trucking in materials that same day. They're dumping them straight into the plants. So controlling this is a very, very difficult process, and that's why we need to make sure that we've got high quality standards in doing that. Importance in aggregate handling, we cannot overemphasize this enough. We can't wear a microphone frequently enough either. Okay, every time we touch the aggregates, it's going to get harder and harder to make sure that we don't have segregation, we don't pick up contamination. So every time the aggregates get touched, we got to make sure that we don't cause another problem. Economy of sampling. All right, there is time involved in sampling. There's also a cost associated with this. Most places that are doing this in terms of production have 1 or 2 people that are dedicated to doing this. I would say that there is a huge value in doing that. We did a survey for the state a few years ago. You could tell the companies that were really looking at quality, they had 1 or 2 or 3 people who did all the testing on a particular job. They had the lowest variability of everybody that was out there because there's inherent variability in how it's done. The impacts can be enormous on terms of the project cost. The penalties can be huge if the materials aren't sampled or tested properly. And unfortunately, what ends up happening is most of the time, these jobs get, the young intern comes out, gets handed a slump cone and gets all the training of go wild and try not to get any on you. We need to make sure that people are trained properly because these can be adjustments that go from the thousands to millions of dollars when you start figuring in incentives and disincentives for speed. Most importantly, they're going to involve decisions based on life and safety. All right? Not all the problems show up immediately. All right? Just because your bridge was standing today when you finished the project doesn't mean it's going to be standing 5 years from now, 8 years from now, 10 years from now. Right? As we mentioned before, daily moisture tests are going to help you in controlling the water to cement ratio and batch to batch water adjustments. Daily gradations are going to help you to meet specifications in terms of aggregate gradations, in uniformity, making sure the concrete is going through quickly. One other thing that I will point out here is ASTM standards that we talked about tend to be very wide standards. They have to be very wide because they have to meet every producer who's producing, while we would say throughout the U.S. or throughout North America, it really also happens to be throughout much of the world. Here you will see the standards that are set by ASTM shown as these yellow bubbles. And here we can see the white bubbles that are established by a particular contractor on one of these jobs. If you really want to control your process, you need to make sure that you're not just taking someone's word for it. Oh, it meets ASTM C33. Lots of things meet ASTM C33. But if you get something that's on the coarse side today and on the fine side tomorrow, you are going to have a real problem trying to control your process. So one of the things that you may benefit from is asking your aggregate producer what they can produce consistently. And then saying, okay, you can produce that consistently. We're going to give you a band. Stay within that band. All right? It may be smaller than what ASTM says, but stay within that band and our concrete will not have problems as we're producing it. Unit weight testing, as we mentioned before, figuring out what a unit weight of concrete is can help you out tremendously with keeping track of your aggregates, keeping track of your air inside of your mixture. So by taking unit weight, the basic idea here, and this is an air test before the air test is done, dump the concrete in here, you can figure out the weight of this bucket full of concrete. You know what the weight of this bucket is when it's full of water. You can basically figure out what the density of this concrete is, what the weight of this concrete is per cubic yard, per cubic foot, and see if it matches up with what you expect from a theoretical calculation. In the homework problem that you just finished up, you notice that it didn't come up to be what we expected it to be. It's a little bit short. That 2%, all right, frequently is going to be traced back to an issue with air or an issue with specific gravity changing your aggregates or too much water being in the mix. There are things that you can do to track this.
What's a good percentage where the plant might be shorting you? Like, obviously 2% is going to be with air, so if you do a test and you think the plant's shorting you, then they can just say there's inherent variability with the air. So what's like a good percentage when they would probably be shorting you?
Well, I mean, the thing is, on average, you should always be back at 1, right? If it's inherent variability, on average, you should be always coming back to 1. Now, I will tell you that there are times where plants do not run at that value of 1. You know, I mean, in a previous life, I dealt with other materials, and I will tell you that we designed to hit a certain number, which was 6.5%, and we never got close to 6.5% because we could run anywhere from 5.7 up, and we could run comfortably by setting our own internal target at 6.1%. Here, what you're going to see is this number varies. When we start to talk about this from a production standpoint, you want consistency much more than you want yield. All right. I think the issue of, you know, if we're worried about them shorting us 1%, in terms of the volume of the material that's out there. I don't think that's the biggest issue. I think what you're really looking for here is variation in the product that's actually being placed. And that's the biggest thing, in my opinion. Now, I'm also not a guy who buys hundreds of thousands of yards of concrete at a time. Right? Again, usually you're going to take the same concrete and you're going to do the air test. The one thing that I would point out is you could use this simple unit weight type approach using the air meter. It's almost free to do this because all you have to do is weigh the bucket. You're going to do the test anyway. You're going to do the air test anyway. It's almost free to go ahead and do it. Some things about sampling. Sample defines a small portion of what you're trying to take. You're looking into the back of one of these trucks. I mean, I will tell you, I would go out there with my little 4-inch scoop, my gloves so I didn't burn myself on the asphalt. I would look at 23 tons of asphalt, and I would try to put my little scoop in there, my little tiny candy scoop, and pull out a representative sample. All right, you want to try to pull out something that is representative of the entire material. All right. The guy that I worked for, he had a famous saying when you would go out there, don't pick a winner, don't pick a loser, pick something that's representative. Almost any good inspector can go out there and pick a sample that he knows is going to win or a sample that they know is going to lose when they come back and start testing it. You want to do all of your testing or all of your sampling to make sure that you're picking something that's representative. And I will point out here that many times you may say, well, I'm not actually doing the testing. I'm just a contractor. Someone else is doing the testing. Many times it's in your best interest to understand the testing procedure so you can correct a testing company or a DOT, and you have to correct in a diplomatic way on how the test is supposed to be followed. No, we shouldn't just scoop up all the rocks that fall to the bottom. No, we shouldn't just take things off of the surface. No, we shouldn't split things by dumping them over the hood of your car. All right, odd things that you'll see people doing because no one has taught them the proper way. Now, why would you try to teach someone? If you're a contractor, your penalties and bonuses are riding on it. It's important to you that they follow the right procedures. Okay. The other thing that I would point out, as we see our dogs here playing poker, this has to be a classy lecture because there's a real fine piece of art with dogs playing poker in it. All right. Finley here gives us the idea that we got to trust everybody, but you're also going to count the cards. All right. Cut the cards. Make sure that you're actually looking at the tests. I will tell you that I worked at different places. One day I wrote up a group for not having done any testing over the last 3 years because there was nothing in their sample books, there was nothing in their log books. The next day I came in and all their log books were somehow up to date, which either means that they are recording them in a special magical place or they are guessing at what the answers are supposed to be. There's another place that I worked, and it was an afternoon much like this where everyone was a little bit sleepy. It was a late Friday afternoon. They had to pull one last batch and run the samples. It was about 4:45, and if you're on the asphalt side, 4:45 in the day is a late day because you're starting at like 4 in the morning to get the materials out. And the technician who was actually performing the test was shouting off the numbers, and I was sitting at the desk writing the numbers down. Well, one of the things that was interesting is I could watch him off of a reflection in the mirror. And he was standing out somewhere near the scale saying numbers. And he had done the test so many times for the last 30 years, 5 times a day, that he had the numbers memorized. And he knew the first number would be somewhere around 1.6. The second number would be around 300. The third number would be around 600. So he was spouting off numbers that had nothing to do with the sample because he'd already thrown it away because he was cleaning up for the day. So you want to make sure that you're actually watching the people do the testing. If you're an inspector, that's what you're there to do. You're there to make sure that they are providing what's important. All right, providing a heterogeneous problems in sampling heterogeneous material. Here you can see that we've got a sample. It's got 70% red. If you pick a small sample, you may get 75%, or you may get 50% red. Sampling, you got to be really careful to make sure that you're taking an unbiased measure. You need to make sure that there's not an influence in how you're pulling these materials out. Frequently, we're going to talk about lots and sublots. This is where we will pick up on Monday. We'll talk about the incredibly important idea of lots and sublots, as well as how concrete can be related to maturity and the temperature and time on your local bank.